Hi, welcome back to College Algebra. Today we're going to look at section 4.5, Exponential and Logarithmic Equations. So we're going to approach these as two separate things. We're going to start with exponential equations, and then we'll move on to ones with logarithms in them here in a little bit. For exponential equations, we first want to start with a theorem. It says if b to the x is equal to b to the y, then that means x and y have to be the same thing. And so notice what's really nice here. If those bases match, we're just going to be able to solve by setting the exponents equal to each other. We'll get to that in a minute. But here's why this works. This is true because if you think about a graph of an exponential function, I have just a generic graph drawn here. Here's some random value of x. So let's call it a. Okay, there's an a. How many y values go with that, right? So, we're looking at, b to the a power here. Well, there's only one y value, and that's it, right? That y value is unique. And I guess, actually, a better way of saying that is each y value only happens once. And so this particular y value only has one value that would give you that y. And so if you have the same base, exponents are equal to each other, or I'm sorry, the bases are the same and these are equal to each other, you get to drop the base. So we're going to look at basically three different kinds of exponential problems. Okay, and so we'll start with some simple ones. Actually, we'll do four examples of exponential problems. We're going to start with some simple ones and we'll move into things that are a little bit trickier and we'll see a variety of different ways you can approach these. So here we go. Okay, so here we have the simplest kind of exponential equation that you can try and solve. You have the same base on each side. Okay, so you'll notice here's my example. Both sides have a base of 3. Importantly, there's nothing else running around in this problem. Okay, it's just one exponential piece equal to another exponential. They have the same base. By the theorem we just looked at, that means that the only way this happens is if those exponents are equal to each other. So you'll notice I jump down to here and I don't have those 3's anymore. I didn't divide both sides by 3. That's not how this works. We are just completely getting rid of them because the only way these two things can be equal is if the exponents are equal. So then I solve this. I subtract my 2x, get 3x plus 6 equals negative 4. Subtract 6 from both sides and get 3x equals negative 10. And when I divide, I get x is equal to negative 10/3. And I'm done. These are really nice ones. So we're going to make it a little bit trickier with the next problem, but it won't be too bad. All right, so the next kind. The next kind is really the same as the first kind, but it's just a little bit trickier example, so I wanted to show it to you. They can be made into the same base. So in this case, you'll notice I have 4 raised to the 3x minus 2 power, and on the other side, I have 32 to the x plus 1. Obviously, 4 and 32, not the same base. But importantly, 4 is the same as 2 squared, and 32 is the same as 2 to the 5th. So I can change these both so that they have a base of 2. Okay, and so if you can see that, it's going to make your life a lot easier. This is going to be a much nicer way to do the problem than the next version that we're going to see, or actually it'll be 2 examples from now that we're going to see. So now I have those 2's, but I need to clean this up just a little bit. I know when I raise a power to a power, I multiply, so I have 2 raised to the 2 times 3x minus 2 power, and 2 raised to the 5 times x plus 1 power. Now I can get rid of those 2's. I just take my exponents and set them equal to each other. I distribute and get 6x minus 4 is equal to 5x plus 5. I subtracted 5x, got x minus 4 is equal to 5, add 4, and x is equal to 9. And there we go. So those first 2 examples are really basically the same sort of problem. In both cases, we can make them have the same base, which is really nice because we can drop the base out and go ahead and solve it from there. The next 2 examples, that won't be the case, so we're going to have to come up with a couple more little tricks. All right, here we go. Okay, so for my next example, we're going to have something that has one exponential piece. So you can see my example here. 5 raised to the x plus 1 is equal to 70. Absolutely no way to make those bases match. 70 is not a power of 5. So we need a different method. The method we're going to use here is we're going to change this out of exponential form into logarithmic form. Now this works really, really well because the only x we have is in the exponent, and when we switch to logarithmic form, the exponent becomes the other side of the equation. So now I get log with a base of 5, but I put the 70 on the inside, and it's equal to x plus 1. So you can see that I subtracted 1. I like to put that negative 1 in front instead of behind because we don't want to subtract it from the 70. That 70 is inside the logarithm, can't subtract there. And then I used my calculator to go from negative 1 plus log base 5 of 70 to 1.64. So I had to use the change of base formula. That was in my last video if you want to go back and check that out. And some of you have calculators that will just do that as is. One other note here, this first line, or this line right here, is an exact answer. Okay, there's no rounding required because we left it as a logarithm. This one is approximate. So be careful and pay attention to any directions you have. You know, if the directions say round to 2 decimal places, make sure you round to 2 decimal places. And don't just cut it off. You have to actually look at that next digit and round it up. I think this was actually a 3 and it got bumped up to a 4. So anyway, that's our third kind. We have one more kind of exponential problem to look at, and it's going to be fun. All right, so here's our last kind of logarithmic problem. 2 different bases. To deal with that, we're going to take the log of both sides. We had a property that we looked at in the last section that said if you have 2 things that are equal, when you take the log, as long as you use the same base, they stay equal. So we're going to take advantage of that one here. So I have 5 to the x equal to 3 to the x plus 7. I can use whatever log I want here on both sides. I could use base 5, I could use base 3. I am choosing to use the common log, base 10, because it is a button on my calculator. Okay, and so I like base 10 and I like the natural log base e because they are buttons on my calculator. And honestly, it doesn't make any difference which base you choose. You should get the same answer as long as you do everything else right. So let's see where I go from here. Now that I've taken the log of both sides, I'm allowed to use the property that says I can drop an exponent down. So I have x log 5, and then I have x plus 7 log 3, but be careful. Notice that with the x plus 7, because it was addition up there, I need that whole thing in parentheses. It's that whole thing, x plus 7, times the log of 3. All right. So then I have to expand the parentheses. I get x times the log base 3, x times the log of 3 plus 7 times the log of 3. Please note, the log of 3 is just a number. You can plug it into your calculator and get it. I like to keep it around until I get to the end because I don't like carrying those weird, crazy decimals. So now I need to get x. I have it in 2 places, and it's attached to these ugly-looking logs. So what are we going to do? Well, I subtracted the x log 3 over to the other side so that my x's were on the same side. Once I get the x's on the same side, I can factor them out. Right? Both terms here have an x. So I can factor it out and have x times log 5 minus log 3 equal to 7 log 3. And then I just finished by dividing by the parentheses, and so you can see I kind of ran out of room here. But we have 7 log 3 divided by the log of 5 minus the log of 3. And that whole thing ends up being equal to 15.05. Now, be really careful plugging that into your calculator. Honestly, when I did it, I typed 7 log 3 and I just hit enter. I got that part of it done. Then I used that previous answer by just hitting the division sign, and it says answer divided. And then I put this whole thing in parentheses. So I put a parenthesis in front of that log 5, and then make sure you, here, let me show you. So I put a parenthesis in front of the log 5. When you hit the log, you get another parenthesis, so I closed that one because we don't want it to do the subtraction first, and then I closed 2 sets of parentheses over here. So play around with your calculators a little bit. Make sure you can get that as an answer, which I am 99% sure is right, and will be very embarrassed if it is wrong. But make sure you can get that, because if you can get that, then you're doing the right kind of stuff with your calculator. So anyway, that's exponential problems. Now we have to go on and look at logarithms. Okay, so the good news with logarithms is that we're really going to look basically at 2 kinds of problems. Okay, I'm going to do 3 examples hopefully, but really just 2 different kinds of problems. The first kind is when you just have one logarithm. If you have one logarithm, we're going to just switch it to exponential form. That will by far be the easiest way to do it. The one thing to watch out for, you can never take the log of something that is negative. Okay, so if your answer would be, when you plug it back in, would force you to take the log of a negative number, you can't have that. It's an extraneous solution. You just get to cross it out. It doesn't count. All right, so here's my example. Log base 2 of x minus 5 is equal to 3. So I switch it to exponential form. The base stays still 2, but now that 3 becomes the exponent, and it's equal to what was inside of the log. Notice now x is not tucked inside of anything. 2 to the third is 8. I add 5, and I get 13. I am going to check my answer. If I plug in 13, 13 minus 5 is 8. That's all I really need to see. You can go further and make sure that it ends up equaling 3, but if you plug it in there and it's positive, you're going to be okay. It's going to work. Okay, so be careful. If this answer were negative, that doesn't automatically disqualify it. You have to actually go back and plug it in and make sure that that what's inside of your log is not negative. All right, so let's go on to the next example. All right, the second main kind of logarithmic problem is when you have two logs that are equal to each other. So I just wrote this as log equal to log. This one's really nice and straightforward. So I have here log 7 of 3x minus 5 equal to log 7 of x plus 10. And the reason this is nice, we had a property again in that last section. If you have two logs with the same base that are equal to each other, the only way that happens is if the inside is equal to each other. So this is the counterpart of the exponential one we did a little bit ago. When we had the same base, just set the exponents equal to each other. Now, same base, we're going to take the insides and set them equal. And then from there, we just solve it. I subtract x, I add 5, I have 2x equals 15, divide by 2, I get 15 over 2, which is 7.5. And if you trust me, when you go back and plug it in, everything stays positive, so we have a good answer. All right, so now we're going to look at one more, and this is going to be a little bit trickier, and yeah, it's going to be fun. Let's see what I have. Okay, so my last example, log 2 of x plus log 2 of x minus 1 is equal to log 2 of x plus 5. 3 logs. So this is why we did that last section. We need to put some of these logarithms back together. I'm going to put these two back together. They're separated by addition, so when I put them back together, I have to be careful. It needs to be multiplication here. If you don't turn it back into multiplication, if you keep an addition sign in between, problem will be easier, but it'll be wrong. So once I put those two back together, now I have two logs with the same base equal to each other, so I can get rid of those and just have x times x minus 1 is equal to x plus 5. I expand my parentheses and get x squared minus x equal to x plus 5. And then I bring everything to the left-hand side because unfortunately I do have a quadratic, so I'd really like to have 0. So I subtract the x to get a minus 2x and subtract the 5, giving me x squared minus 2x minus 5. And then over here you can see that I did the quadratic formula. It was loads of fun. Be really, really careful. I'll let you sort your way through that because I'm running short on time before YouTube cuts me off. But anyway, the big thing I want to point out here is at the end, we have these two solutions. You'll see I found that they're approximately 3.45 and negative 1.45. So remember what I said before. We can't have any solution that would force us to take the log of something negative. I think pretty clearly this is a bad candidate right away. We can see it in the very first log we find. That's a negative number. If I plug it in here, that's going to force me to take the log of something negative, which remember we cannot do. That one is extraneous, so I'm just going to get rid of it. The other one is going to be just fine. If I plug it in there, it's a positive. 3.45 minus 1 is still positive. 3.45 plus 5 is positive. Those are all positive. That's my only good solution. So the question is, very quickly, why do we get an extra solution? Well, it happens right here when we put them back together. Remember what we know about multiplication. When you multiply two negatives, what do you get? You get a positive. So right here, when I put them back together, I'm taking that negative potential solution, but a negative times a negative is a positive. And so we introduce that possibility that what we have doesn't work. So anyway, there you go. That's exponential logarithmic equations. Have a great day.